Hello, everyone. Welcome to this session. My name is Hongcai from Huawei, and I'm one of the maintainers of our Karmada project.
And I'm Jai, I work at Bloomberg at our Cloud Compute Services platform team. This is our agenda for today. First, Hongcai will do an overview of Karmada and some of the features that it provides and cover some of the key use cases. Then I'll do an overview of some of the use cases that we have at Bloomberg, how we build a managed service to support those use cases. And then I'll switch it back to Hongcai, who will talk about community growth and ecosystem integration, as well as current activity and roadmap for the Karmada project.
Okay, I will give a brief introduction of Karmada for those don't have the context about what Karmada it is and what problem it solves. Karmada is a project that designed to manage application across multi-cluster, and most of our users are using Karmada something like a CD system. They deploy workloads to Karmada, and Karmada helps to schedule the workload to one or more clusters. And after the resource has been propagated to multi-cluster, the administrator might need to have a global view of the resource, and so we support that the resource can be reported to a third-party database like Elasticsearch or OpenSearch, and so they can build a global view of the resources. So another fancy feature is failover. The failover includes class failover and application failover. For the class failover, if one cluster crash or shut down, Karmada can migrate the application from this cluster to another. And for I just said the application level. The application level that Karmada can watch is your application running in single cluster, and if the job crash or crash, Karmada can migrate the application to another cluster. Yeah, I just told the cluster server. Okay, as you see in previous slide, Karmada has a lot of components. As much as the Kubernetes is it's not that easy to maintain so many components. So Joe will show their practice to run Karmada. Okay.
Okay. So I'll cover some of the use cases that we have for multi-cluster federation at Bloomberg. We have many use cases. Then I'll do an overview of how we build a managed service to support those use cases, followed by some of the contributions that we made back to the Karmada project that have had direct impact in the development of that managed service. So I'll start with this one, which is a more general one. It goes something like this. We want to reliably propagate resources, such as config maps, secrets, cluster workflow templates, and workflow templates, to a set of clusters. This is another one. This is a very hot one. To accelerate AI inference, we want to federate model cache resources on GPU nodes across a set of clusters to reduce model warm-up time. I have one more, or there's a few more. We want support for stateful application failover to improve Apache Flink workload resiliency on multi-cluster Kubernetes. We actually had a talk about this use case yesterday. And I'm going to sound a little bit biased, but I think it was pretty amazing. So if anybody missed it, I would strongly urge that you watch the recording. There's one more. We want to optimize GPU utilization for AI model training across heterogeneous clusters. This is also a hot use case, and we also have a talk here at KubeCon for this use case. Unfortunately, it's a concurrent talk happening right now, but I would also strongly urge everyone to check out the recording. Okay, so now time for the big question. Given that we have all those use cases for Karmada, how will all those teams use Karmada? So at a very high level, we basically have two choices. Choice one, doing it yourself, where each team will build and maintain their own Karmada-based multi-cluster infrastructure, which is not a trivial task. Or, maybe some of you know where I'm going with this already. Using a paved path where each team will offload management of Karmada multi-cluster infrastructure to some magical managed service offering. And on my team, we build this managed service offering. So I'll take you through how we did that, starting with the most basic setup and gradually building up to what we refer to as stretch Karmada. So to start, we build what we call the host cluster, host or management cluster. And throughout this talk, I'll use the terms host and management cluster interchangeably. Then we install the Karmada operator from the upstream Karmada project in that host cluster and use that operator to provision a base Karmada control plane. However, at this point, there's still some more work to be done, as the promise of managed Karmada is for everything, including ingress traffic, to manage Karmada control planes, as well as fully automated and dynamic member cluster registration to just automatically work. And to make that happen, we built our own operator, the managed Karmada operator, which integrates with our internal systems to set up ingress traffic to manage Karmada control planes. And we'll also install the cluster registration subsystem that integrates with our internal systems for fully automated and dynamic member cluster registration. In that subsystem, we have the cluster provider component that integrates with our internal cluster inventory API to dynamically sync cluster state for managed Karmada control planes. We also have cluster credentials provider that integrates with our internal token exchange service to provide Karmada with the credentials that it needs to push work to registered member clusters. Karmada also has an add-on called Scheduler Estimator that, when enabled, will help to inform the Karmada scheduler on how workload should be federated across the set of registered member clusters for a Karmada instance. When enabled, there must exist one scheduler estimator instance for each registered member cluster. And our scheduler estimator provider will handle provisioning of those scheduler estimator instances, as well as all of the plumbing required to make that feature work. So at this point, we have successfully provisioned a Karmada control plane for a tenant. So now let's go through some of the scenarios to see what type of failures we can withstand with this topology. The first one is failure of a member cluster. For this tenant, we have a control plane that's joined to two member clusters. So if we have one member cluster failure, then we can still maintain continuity of service as workload running on that failed cluster can be migrated by Karmada over to the other member cluster. However, if we lose our management cluster, given that this is the only management cluster we have, then all of managed Karmada will be out. This is a big problem, as our tenants will rely on managed Karmada to power mission critical workload. So we have to solve this issue. To do that, we get a bit more fancy and introduce what we refer to as the stretch topology. In this topology, we now have multiple host or management clusters that span multiple data centers. Then we take the Karmada instance and stretch it across that cohort of management clusters. Integrate with our DNS-based load balancer managed service to provide one unified ingress endpoint to each managed instance, and also integrate. And for that to work, we ensure that the same CA certificate is used to provision the instance on both host clusters. Then we integrate with our managed SCD offering to provision one multi-cluster etcd instance for the managed Karmada instance, and ensure that the instance on both host clusters connect to the same etcd cluster. And now, in this topology, if we lose a member cluster, we can still maintain continuity of service as the other member cluster will still be up and running. And if we lose a host cluster, we can still maintain continuity of service as the other host cluster in the data center will still be up and running. If we lose an entire data center, we will lose some of the members of the etcd cluster, as well as the some of the members of the etcd cluster, as well as the host cluster running in that data center, but can still maintain continuity of service, as we will still have quorum for the etcd cluster, and we'll still have the host cluster and the other data center still up and running. However, if we lose both host clusters, then managed Karmada's out. And this one should be self-explanatory, but I'll vocalize it anyway. If we lose both data centers, then managed Karmada is definitely out. However, those two last scenarios should be very, very unlikely. So if we ever get to this point, then I think we will have much bigger problems to worry about anyway. So now let's look under the hood to see how the stretch topology works. We start by installing what we refer to as our central source of truth. It's a minimal control plane with Kube API server, controller manager with a subset of the controllers enabled, as well as cert manager components. And it's installed stacked on our cohort of host clusters. We then again integrate with our DNS-based load balancer managed service to provide one unified ingress to that central source of truth, and also integrate with our managed etcd offering to have that source of truth backed by one multi-data center etcd cluster. Then we install the operators. We have the source of truth operator, the managed Karmada operator, and the sync operator. At this point, when our custom resource is applied to the source of truth API server, the source of truth operator listening to event sources from that API server will do a few things. It will connect to our managed etcd offering to allocate an etcd cluster for the Karmada instance. It will also provision the API server CA certificate that we need to make unified ingress work for the stretch instance, as well as other things like provisioning of a client certificate for the Karmada control plane. Then the sync operator, which also listens to event sources from the source of truth API server, will sync all of those resources from the source of truth API server to the host cluster API server. At that point, the managed Karmada operator will have everything it needs to provision that instance on that host cluster, and will do just that. And the same process happens on both host clusters. Okay, so the promise of a managed service like managed Karmada is to handle all of the complexities of multi-cluster infrastructure, so that from our tenant's point of view, use of Karmada is trivial. And a good way to look at how that's achieved is by looking at the process for tenant onboarding. It's a very trivial two-step process. First, we will create a tenancy for that tenant. That's basically a custom resource. And once the tenancy is provisioned, we will then privilege the tenant, give the tenant access to create Karmada control planes in that tenancy. And that's also just another custom resource. That's already pretty trivial, but we made it even simpler than that. So this tier resource that you're looking at is one of the resources that's part of our cluster inventory API. And it's a resource that our tenants for managed Karmada already own. So to simplify the onboarding process even further, given that the plane is for each Karmada control plane to be joined to member clusters belonging to a tier, we build a first-class integration that empowers our tenants to declaratively define the desired state of a Karmada control plane that should be automatically join to member clusters belonging to that tier directly as part of the tier resource. And that's exactly what you see on the right. Very trivial process. Okay. For the last segment, before handing it back to Hongcai, as part of Managed Karmada, we've also worked very closely with the Karmada community on numerous open source contributions that have had direct impact for the development of Managed Karmada. So I'll go through some of them. So the first one, as part of provisioning a control plane, the Karmada operator needs to install CRDs. And by default, it will download those manifests from some release artifact on GitHub. Unfortunately, this approach cannot work within an air-gapped environment like ours at Bloomberg. So to remediate that issue, we made a contribution back to the Karmada project to allow support for using a custom HTTP source for downloading those CRD manifests, which will work within our air-gapped environment. This is another one. So this one added support to the Karmada operator for configuring the priority class of managed Karmada control plane components to ensure reliability and stability of managed Karmada control planes. This is another one. This is the one I talked about earlier. So in one of the diagrams I showed earlier, in the stretch topology, we have the Karmada instance stretch across two, or it can be two or more actually, host clusters, but accessible via one unified ingress endpoint. For that to work, we have to make sure that the same CS certificate is used to provision the instance on both management clusters. And this contribution added support for configuring the Karmada operator to use custom CS certificates. Okay, I got another one. So one of our requirements from our tenants for Managed Karmada is for configuring encryption at rest for confidential data. There's quite some optionality for how you can configure that for the Kube API server. But one highly recommended approach is to integrate with a key management service. If that option is chosen, then there must exist a KMS plugin that runs alongside the Kube API server to bridge that integration with the key management service, as the Kube API server will have to connect to that plugin via gRPC for encryption and decryption request. And this contribution added support to the Karmada operator for API server sidecar containers to enable that integration for us at Bloomberg for our internal key management service. It's another one. So by default, the Karmada operator, as part of provisioning a control plane, will set up public key infrastructure with the leaf certificates in that infrastructure having a default validity period of 1 year. So to align with our organizational security policies and certificate management policies, we made a contribution back to the Karmada project to make that configurable so that we can configure the validity period of those leaf certificates as we please. Okay, so one more. I think we're close. So the way Managed Karmada work is we make use of the Karmada operator, but also have our Managed Karmada operator, which integrates with our internal system. And the way it works at a very high level is that our operator will offload work to the Managed Karmada. Our operator, the Managed Karmada operator, will offload work to the Karmada operator for provisioning a base control plane. And once that base control plane is ready, we have to do other things like setting up ingress traffic. And this contribution added support to the Karmada operator for reliably discovering the API server service for configuring that ingress traffic. Okay, one more. For Managed Karmada, we integrate with our managed etcd service to allocate one multi-data center etcd cluster for each Managed Karmada control plane. And this contribution added support to the Karmada operator for using external etcd clusters. Okay, one more. I think this is the last one. We have a set of requirements for our tenants for managed Karmada, and that includes the ability to integrate with our internal off and webhook service for authentication, as well as for configuring encryption at rest. With existing support in the Karmada operator for specifying extra args, we made a contribution to also add support for extra volumes and volume mounts to unlock those use cases. My favorite part of doing this is live demos, but unfortunately we don't have enough time, so I'm gonna pass back to Hongcai.
Okay, thank you, Joe. Joe has made a lot of contribution to the project. Now Joe is the maintainer of the Karmada operator, right? Yeah, thank you. I want to talk about the Karmada community. Karmada was open source at 2021 and became a safe sandbox project at the same year and moved the levels to incubation at 2023. Karmada joined the efforts of more than 700 contributors, and we have we build a fast growing community, and for now we have 36 public adopters. They run Karmada in production, and some of them are use Karmada for managing quite large scale of clusters. So this year we are still focused on AI training job, inference jobs. For now, I think Karmada can support the training job quite well, but we still have some corner case we need to handle. And for Karmada operator, I believe we gonna have more enhancement need to do, right? We also have two team for performance enhancement. They will focus on improving the performance, the scalability, and another team is for the Karmada dashboard. A lot of users need a UI for manager Karmada. That's all. Thank you. We still have some time, right? Okay, thank you. So I think we can.
We have time, yeah.
We still have some time, so if you have any questions. Okay, take silence as none. Okay, but I and Jill will still here for a while. So if you gonna ask, okay,
hi,
sure.
Yeah, sorry, I joined kind of halfway. So amazing presentation. I'm sure I'll catch the first part. How does Karmada compare to Q, for example? What do you say is like the different feature sets?
I'm sorry. How many Karmada? What?
No worries. So how does Karmada compare to Q as a multi-cluster orchestrator?
Okay. Firstly, I think Q is the project that provides the queue management in single cluster. Karmada was designed to handle the problem with multi-cluster in the first place. So I think that's the big difference between them.
Hello? Yeah. So you're saying that it's a bit of an afterthought maybe for Q, that it was initially a single cluster tool, and I see they have like a leader queue with multi-cluster support, but you're saying actually Karmada out of the box is trying to support multi-cluster management, and that's kind of the differentiator? that what you're saying?
Sorry.
No worries, no worries. Am I speaking too fast? Yeah. Cool. So what I mean is, are you trying to say that Q only provides multi-cluster support as a secondary feature, whereas Karmada, like that's the main kind of selling point for Karmada?
You're asking multi-cluster queue, right?
Yes, yes.
Yeah. We have thinking about it for a while. First, we are trying to do is to integrate queue, maybe integrate Volcano as well, because they both provide the queue in single cluster. So we are trying to integrate them for Karmada user to manage their jobs on multi-class area. So we'll see how it works. Yeah, I think we are working on it. But for now, actually, Karmada community and Volcano community have already worked together and provide a solution for multi-queue named Volcano Global Product.
Nice.
You can have a try.
Thank you. Yeah, I'll do that. Well, and also about Kubeflow. Is there any sort of integration with Kubeflow pipelines?
Sorry.
All good? Yeah, I'm here.
Okay.
So does Karmada have any integration with Kubeflow pipelines?
Kubeflow.
Yes.
I think Kubeflow for Karmada is just a set of CRD. Karmada has full support for any kind of CRD. So I think I don't see any gap to run Kubeflow on Karmada.
Nice. That's perfect. Thank you so much.
So, thank you all. Thank you for your time.